Okay, welcome back to EL164. Today we're going to be talking about timers. Timers are used quite extensively in PLCs. This is today we are in week 4, starting with chapter 7. Programming timers. One of the things that the book does pretty well is defines how timers are used in the RS500 version. It has a really weak section in chapter 15 part 3 about timers. It's like 3 pages long or something like that. So whereas this chapter 7 goes into a rather in-depth on the process of how timers work. And so we drop back to chapter 7 for timers so we can get that in-depth feel for timers. Addressing is a little bit different than what we see here on the page, but we'll be going into that as well, so you'll have a solid understanding. But when you're dealing with the 500 world, the T4 is designated as the file number for timers. In the 5000, we can call it whatever we want. We can call it Joe's timers or Fred's timers, whatever we wanted to call it. So it doesn't have to be a T4 designation. Though the word and bit allocations are still fairly close to the same. As you can see here, they have a control word, a preset word, and an accumulated word. We have the same thing set up in the 5000 world, only it's a 32-bit word, and of those 32 bits, there's again 3 bits used to the control word. That's the done bit, the timer timing bit, and the enable bit. Brief review of mechanical timing relays. They make several different styles. I've used mostly something that looks more like this guy over here on the right, where you have a little knob on the top and some little selection of how you want to set up the timing. Something to be aware of is a lot of these type of devices will cost the same, if not more, than a little micro PLC. And so the use of these are getting used less and less all the time, just because the flexibility of a micro PLC, or they even call them smart relays, where you got if we were in the lab, we would see it was called an 810, which is basically a relay with some push buttons on the face of it and a digital display. It allows you to set up things like timers for relatively inexpensively, as well as a pretty easy setup. Here's some of the schematics and whatnot associated with the mechanical timer. You can see here they've got the normally open, normally closed contacts, and then they also show some timed contacts where the arrow points the direction to when the timer is done timing. This is the direction the contact moves. So what it's saying basically in this particular case, this would be considered to be a normally open terminal, but closes when timer is done, and a normally closed terminal that opens when timer is done. So again, online, on delay or off delay relays are both available, and here's some of the more of the schematics associated with those. So that's what they're referring to. Okay, so when S1 is closed, the TD is energized and the timer period starts. Once the after it has lapsed, the L1 switch is closed, switches on. So here we are, normally closed timer on contact. Again, same idea. That input turns on and then the output goes from an, because it's normally closed, goes from an on state to an off state, is what they're showing us here. Same principle of the off delay. The difference with the off delay is when it sees this contact come on, the output or the output of the timer turns on immediately, and then when the when the input turns off, that's when the timer starts timing and keeps the output on for some period of time that you have selected. At that very point when it reaches that time, it turns off. The output of the relay turns off, or the timer turns off. So normally closed timer contact here. Again, same idea. Is we come in, we see this guy come on, so it actually goes from an on state to an off state because it's open. It opens it because it's normally closed, and it stays open until it reaches the timer done. At that point, it turns on. So timer instructions, where are they found? All that business. So here we are on the on this board here. You'll see the timer on, timer off. These are the two components that we find under timer counter title in the PLC. Again, we're looking at a 500 version here. 5000 is very close to this, and when we get into lab, you'll see just how close this is. It's identical. So timer on, TON is timer on, TOF is timer off, and RTO is retentive timer on, which requires a reset, an external reset, and we'll be getting into that here shortly. So associated quantities, or quantities associated with the timers, they got the preset. The preset is the amount of time we're going to be timing for. The cumulative time is the amount of time that has elapsed, or it's kind of the timing value of how long the time has been taking place. And then the time base is not really used in the 5000, so we're going to kind of make you aware of time base is the value of which in the 500 version, that value of how many seconds or milliseconds, or so it gives you the 0.1, I think it's 0.01, 0.1, and 1. So you can switch it to vary in different times. So if you wanted to measure seconds versus milliseconds versus all these different things, it gives you different tools to use that for. But the 5000 only uses the millisecond base time, so we're only going to focus on that. This is kind of an older version of a timer. You'd see the little coil that looks like a timer, but it's not. A nice neat little box that they have now. But here you got the address, the preset, and then the base value that we mentioned earlier that we really won't even see in the 5000, and then the accumulated value. So here's something more along the lines of what we'll see is a box with a timer in the front of it, and let's get nuts and bolts of that. Okay, so here now this is kind of what we're going to be looking at in a PLC is a timer, is an input to it. As that input closes, when this is closed, we go from an all false to a true statement. At that very moment, you see the time period, the time from when it goes true, and then the time on delay duration after it's gone through. At that very point is when the output turns on. Again, as I mentioned before, this is the addressing for the 500. We will be seeing something very similar to this, but it'll be, instead of T4, it'll be timer. It'll be we'll just call it timer. And but there is some very similar things. It does require 3 words: a word 0, a word 1, and a word 2. Word 0 is called the control word. The word 1 will be called the preset word, and word 2 is accumulated value. The enable bit is true whenever the timer's instruction is true, so that that we can count for turning on when the timer is timing, or timer is enabled. Excuse me. The timer timing bit is true whenever the accumulated value of the timer is changing. So as long as we're incrementing that timer, that's when that bit stays on. The done bit changes state when the accumulated value reaches the preset value. So you think of it in the sense that when this accumulated value here is equal to the value here, say they got T4:2 highlighted here. So when this value equals this value, then at that very point, the done bit would be on. This is kind of what it looks like here in the logic. So you see a couple pieces here. The timer address, the timer base, which again we're not going to see in the 5000, the preset, and the accumulated value. The preset word is a 32-bit word for us in the 5000 version. It's a 16 here. And the accumulated value, again, is a 32-bit word, giving us a lot more range. So there's that. So here we are looking at the same thing here. The T4:0 is the address. The time base, again, you've got multiple options here that we don't have in the 5000. Preset value is 15 in this case, so that's the value you enter into that timer. The accumulated value at this point is 0, so there hasn't been any accumulation of time on this timer. So here we enter, when we're developing this device, we enter a timer address, a preset value, and a accumulated value. So we can enter whatever we wanted for a preset value, even another register if we wanted to. And this, oh, by the way, is in a 5000. This is exactly how that lays out. So here they're just showing us an example of when you use a timer. So you got input A. When input A closes, the timer will start timing. T4:0.en, or this basically this call here, will turn on as soon as A turns on, which will turn on B. And then after the accumulated value and the preset value are on, oh, I'm sorry, the timer timing bit will start timing the second this starts incrementing. As soon as it goes to 0 from 1, that timer timing bit will come on. And the done bit will turn on when preset equals accumulated. So timer on instruction. So in the when it's off, accumulation, no accumulation, all these bits will be off. When it's on, you'll see the enable bit, the timer timing, the done bit will be off, and it'll be accumulating. Timed out, you'll see the enable bit on, the timer timing bit off, done bit on, and no more accumulation. Instruction off, after time off, then again, everything will be reset to 0. What they're indicating here is that the value of the accumulator will be reset to 0 when you remove that signal to the input. And here we are with an example of how that's going to work. Notice it's counting to 100. We've got timer enable and timer timing both on. We reached 100, timer timing turns off, done bit turns on, allowing for 2 to turn on. So watching it closely, enable and timer timing are both on. And when the done bit, when this reaches 100, the done bit will turn on, timer timing will turn off, and we'll sit there. We turn off the input, that now accumulated value resets, enable, timer timing, and done bit are all reset. Okay, so here's a mechanical or a hardwire versus a PLC program, and using that timer. Again, keeping in mind these are, that's a normally closed push button, a normally open push button. When these two contacts, when you close this guy, that timer timing will start timing. When that done bit turns on, that closes that contact. And here's the same thing done only with a PLC program. As you can see, one of the aspects of wiring for a PLC is way easier. Just got a point-to-point wiring, where here you've got to wire here, from this point to this point, this point to this point, this point to this point, and so on. You can see a lot of terminal points here, a lot of room to make errors one way. So here they're going to give us an example of what it looks like running. So I put a 5-second delay on the motor starting here. And this is actually an exercise that we get into in 166 a little bit. So it's kind of cool. So here's another example of how a circuit in a hardware program, you can see the seal-in circuit here. We turn on this guy. When that guy turns on, he turns on the timer. The timer looks like it starts the horn immediately. When the timer times out, then it opens up that circuit, turning off the horn. And here they did the same thing, only using a little bit of logic. Kind of cool. So after 10 seconds, the horn turns off. As you can see here, they seal this information in, so that EN is sealed in, so that this timer stays active even after you reset the startup. It's not until you hit the reset button, which is normally closed. When you press that button, it opens this off and turns that off, and resetting everything. So here's something that they're looking at sequencing some motors and whatnot. This is a very common practice. Using a hardwired circuit, not so common anymore, but PLCs for sure. Also here, basically what's going on here is as soon as you see the main motor drive turn on, it looks like they've got a timer here. When that timer has been on for 15 seconds, at that very point that it closes and turns the feed motor on. And here's the equivalent to that using the PLC code. Noting that they got the T4:0, right, the correct address, and the done bit. The done bit is the most common bit to use on a timer. That's the one that tells us when it's done timing. And here's another example of that. This time we gotta wait 15 seconds. 15 seconds. Motor 3 turns on. And then we hit the stop button and it resets that guy. And they turn off the pressure switch and it turns off the motors. So, off delay timer. Okay, so now the off delay works very similar to the on delay, only a little bit differently. So the key point that most everybody gets confused with on the off delay timer is that when the input for the off delay timer comes on, the output turns on immediately. The done bit turns on immediately. So watch that done bit. See when this guy comes on, comes through, the done bit turns on immediately. Now when it starts timing is when the input turns off. That's when it starts timing. And the done bit stays on until the timer is done timing. At that very moment it turns off. And here's an illustration of what that timer looks like. A TOF is the illustration for, or the timer off program or command. And so here we're looking at another application where we got a switch in front of a timer off. And here's an example of how that's going to work. See how that done bit stays on after he's released the input. That's off and it's still timing. It's going to reach 150 and then it's going to turn off, turning off this output. As soon as he turns it on, the done bit turns on. As soon as he releases it, it starts timing. It does not start timing until what? Till you turn it off. It resets it to 0. When you close it, and reaches 150 and it's done. So here's an application where they put multiple motors together again, and so we're switching motors off at 5-second intervals. So you got T41, T42, and T43. Each one's got a different timer value to it. So here's the states of the timer off. In the on state, you will see enables on, done bit is on, no accumulation. When the instruction in front of the timer is off, the enable is off, the timer timing is on, the done bit is on, accumulating, yes. Timed out, that means we've reached the end, so everything goes to a reset state. And an instruction off after timed out. So the enable's on, the done bit's on, and the accumulating is reset. So that's pretty much the status of the off delay. And here we are. First timer is timed out. Second timer is timed out. And the third timer is just timed out. So here they're showing a timer that has essentially instantaneous and time contacts. So these would be the time contacts, these would be instantaneous ones. So that would be like a relay. Some contacts are made immediately, like in a relay. And then the timer aspect of it is the timed contact. So here they're trying to show us an example of pumping fluid from tank A to tank B. PS1 must be closed. And then, okay, so here we've got an example of this. So we got start, the stop, and the pressure switch here. So to turn on the pump. So the pump has to be on for 5 seconds before we turn on the off delay. Let's take a look and see how that works. Okay, so now we're getting this guy to click on, 5 seconds on there. And the off delay here. Not a really good example, but a lot going on here. It's kind of hard to follow, but you get the idea. You can see the pump time and the pump delay here. Retentive timers. Okay, so now these are the timers I was telling you about before. They kind of maintain other information, so they require an external reset. So let's take a look at this. Here's our showing how a mechanical solution to that very same thing. Retentive timer requires a reset. Notice the reset has the same address as the timer. In the 5000 software, it uses the same principle. You got to have the address has to be the same for both the reset and the timer. In this particular case, you've got a lot of the same things. You got a preset accumulated and a control word. The timer timing, timing enabled, timer done. That's available to you. And here they're kind of show us an example of how that works. So here we have, I'm going to call it PB2 is a reset, PB1 is a retentive timer. So as we're holding this guy down, it's going to hold that information. We turn it off. It's going to maintain that information until we hit the reset. So this one retentive timer does not reset to 0. When you remove the input, it only resets to 0 when you hit the reset. So what they're trying to show us here is how it increments and whatnot using the enable. So we essentially when your time input is true, your timing, and then it stays true until you hit the reset. So when you hit the reset down here, it goes back to 0. But otherwise, it just keeps incrementing up. And here's an example of how that works. Noting every time he releases that push button, it increments the timer. He's holding it down, his timing. And when he hits that reset button, it resets it to 0. Resetting it back to 0 when he hits the reset. So here's another application where they're using a retentive timer to turn on a horn. Notice how the accumulated value down here and the preset values are all set down here, and then you can see actually you can even see the bits take place down here. The enable bit, the timer timing bit turning on in the data table. I put enough time on this guy. 60 seconds. Holy mackerel. And finally, we reached the done bit on that, so we're good. So now I'm going to bet it's probably nope, you hit the reset. Okay, there you go. Reset it back to 0. And look at us try that one. Bearing lubrication program. Okay, so here, this is a good example. The bearing. This is quite often you'll get into lube applications. One of the common applications that I get run into is lubing a press. And what they wanted to do is they wanted a shot of lube to the main bearing of a press after so many cycles. So what I would do is I would put a counter in there and count the cycles of the press. When the press reached that magic number of whatever 500 hits or whatever happened to be, they needed the lube to turn on and a pump for like 3 seconds or something, or 5 seconds. And so what I'd do is I would trigger, I'd hit the count of 500, say, trigger one shot, and that one shot would trigger the off delay timer. So that one shot turned on the off delay timer, and the off delay timer would be set for 5 seconds, and it would lube the shaft for 5 seconds. Works pretty good. Man, they put enough big numbers on these things for an application here, but we get the idea anyways. So we'll reach the timer on. Now we're going to hit the timer off. Now it reaches 150. That done bit is going to turn on, and then there's flipping it back again. And now they're monitoring the pump, how much time the pump has ran all together. And then when that reaches 600, of course, then that light will turn on at that point. And we're in business there. Okay, moving along. Cascading timers. Now, cascading timers is something that I've used quite a bit of as well, where you can you have one timer, timeout, to time another timer, to time another timer, so you can go for a longer length. With the 32-bit format that the new 5000 offers, not so much of a need for cascading anymore. But back in the 500 days when there was not as big a number we could put into a timer, it was more of an issue. So I don't think you'll see too many cascading applications anymore. But here's a particular application here where the T4:1 dot done turns on the T4:2 dot done to bring in the M3. And boy, they put a lot of big numbers in these things. So here we got to count to 200. We reach 200, we're going to turn on M2. And then when we reach 200 on the second timer, we're going to turn on M3. Seems like they could have gone a little less than 200, but 20 seconds is a lot. Okay, M3, there we go. You're going to do a reset probably, okay. All right then. So, a flasher circuit, this is probably one of those circuits that you're going to see time and time again. Flasher circuit. There's other ways to do the flasher circuit. This is probably one of those common ways. You notice here, the T4:5 is normally open down here. The T4:6 is normally closed up here. So essentially what will happen is this timer here will start timing. We'll get to 1 second. Close this guy. It starts this guy timing. When this guy reaches 1 second and he opens up that guy, which drops that guy out, and he starts timing again. So you end up with a it's kind of cool. Let's see what the example has for us here. Noticing how those timers are flipping back and forth. 10 seconds, 10 seconds. This one's hitting 10, this one's hitting 10, this one's hitting 10, this one's hitting 10. Back and forth. Flasher circuit. Notice that they didn't put anything else in these rungs. They just let the flasher flash, and then they're implementing what they need to flash when external inputs down here. Very common practice. You try to not interrupt these flasher circuits. You want them to just flash back and forth at a steady rate. So just so you don't put any contacts or any information in these rungs except for the timer value that you need in each. So as I mentioned before, this is a pretty common case of cascading timers with longer time delays. So you can put bigger values here and end up with a longer. So this guy times reaches this value, that's done. This times reaches this value, then that's done, and then it turns on the output. So hopefully our example is not 3 days long. 10 seconds is plenty per timer though. So here we are, we got the first one counting for 10 seconds. That's going to come done. Start the second timer starting for 10 seconds, and then when that one reaches the done bit, then we'll have a whole total of what? 20 seconds. If you can imagine, if you were trying to do this for 2 hours or something, or 2 days or something like that, you would need a lot bigger numbers in here. And because this limitation with the 500, we couldn't go with really large numbers. Well, again, with 5,000, we can do that very thing. So here we're looking at some, looks like a T4:0, red time, green time, and amber time. They're just setting up some different light applications here. So they're saying for each traffic light, we want it to be on for, first one for, shoot, this monkey, 30 seconds. Second one on for 25 seconds, and the third one on for 5 seconds. So here we got the green time. Now we're reading green for 25 seconds. So when he goes done, he's going to time here for 5 seconds. And then at that point, we go back to red. So decent application. Again, this will be something we'll see in 166 with the programming simulation that we'll use in there. Cool one. So they're getting into a little more advanced stuff with the timer, showing us lights in 2 directions. So how you can go about doing it. Okay, so here's an that same application. They just expanded a little bit, adding an extra light. Here, they got a lot of time on these delays and whatnot, so let's take a lifetime to get through this slide. So anyways, this is the last slide of the timers. I'm going to jump over to the couple pages they have in the 5000 just to reassure the information there with you. So that'll be a real quick jump into that. But this is it for the chapter 7 timers. Okay, thank you very much, and we'll be talking to you soon. Bye bye now.